All right, we're looking at hyperbolas. Now, a hyperbola is probably the strangest of the conic sections. Hyperbola is defined as the locus of all points in a plane such that the absolute value of the differences of the distances from the two foci is constant. All right, so there are still two focuses, okay, very similar to our ellipse. Now, any point on our hyperbola is going to have the same difference in the distances as any point on the other. Well, essentially every point, any point, if you measure the distances to the two foci and find the difference, well, it's going to have the same difference. It is the same difference in the distances. So if the difference between these two distances is 2, then they're all going to have a difference of 2. Like that. Now, when we're dealing with a hyperbola, it could be opening vertically, it could be opening horizontally. The vertices are connected by what we call the transverse axis. Yeah, transverse axis. The center is where the transverse axis and the conjugate axis intersect. We still have a focus, and the distance from the center to the focus is our C value, and I don't believe we say it on here, but C is equal to the square root of a squared plus b squared. So yes, C in this case, where in an ellipse, C was a squared minus b squared. But C squared here is Pythagorean theorem, a squared plus b squared. That's what we wanted. That's what we want. That's C is equal to the square root of a squared plus b squared. So C is, once again, the distance from the center to the focus. The distance from the center to our vertex is just A. And the B value does tell us the distance from the center to the side, to the end of our conjugate axis. And that is going to be pretty helpful to us, believe it or not. Okay? Okay, C squared is A squared plus B squared. Good. This is how B can help us out. Okay, so here, in this case, the vertical axis is our conjugate axis. Our conjugate axis does not go through the vertices. And it stops right here at our B values. Positive B, negative B from our center. And we know our vertices are a distance of A out on each side. And so that point right there going through our center helps us to find the equation of our asymptote. Same thing with this. There's two asymptotes here, and we can find the equation of that by looking at these 2 points. The point that is the center of our hyperbola and the point where our A and our B intersect. Very helpful to us, very helpful indeed. So, take a look at all of that. And like I said, I would think about the asymptotes as I was just talking about them. This, I think, overcomplicates the asymptotes quite a ton. Notice here, A squared does not have to be greater than B squared. A does not have to be greater than B. A is whatever is the denominator of our first term. Because the order does matter, we're subtracting. This is x minus h squared over a squared minus y minus k squared over b squared. Now, the a, of course, affects where our vertices are for hyperbola. And if a is affecting h, then we know that, if a is affecting the x term, we know it's affecting the left and the right. That means our hyperbola is going to have a horizontal opening. The opposite is true if y is first. If it's y, the term with y minus the term with x, then we know A is affecting the y term, which means it's that vertical opening. So all that pretty much affects like we would probably expect. All right, so intro to hyperbola. Now we'll look at some real graphs.